We've almost made it through the first week. Wahoo! So, I had a couple of just real quick things to say before you view today's lecture. One is I'm really excited. I just got a new student in class. So, yeah, I'll show you. Look at that guy. Santa Claus. A little bit disturbing Santa Claus. He's got handcuffs on because he was doing some stuff. Put him in the front row. So, other than that, though, I'm pretty excited. Make sure that as you're, especially when you get to the second section of this video where I look at, or I kind of do some problems for you on a whiteboard program that I've located, make sure that you have some of the resource guides with you, either printed out or available to you. And the two that you're going to need are the hydrocarbon prefix guide and also the hydrocarbon drawing naming material. And so hopefully if you have both of those for the whiteboard section, which is the second part, those will be super helpful to you. I'm going to do kind of a quick introduction PowerPoint that involves just kind of like the naming rules that we'll be seeing, a couple of different types of structure drawing that we'll see when we're drawing organic structures. So without further ado, to start off with, this is a presentation that I generally show my classes when we first start naming. It's just a really good introduction. I won't be going through all of the slides in here because honestly the easiest way to learn how to draw and name structures is just to practice. So oftentimes when you name a hydrocarbon, that's called nomenclature. So here's a little benzene ring being baptized. So a couple of things that we just have to be real clear about. So here's a typical name, right? A couple of things you might recognize about this. First of all is you've got the but, right? Which should tell you how many carbons are in something. And also the ending is going to turn out to be pretty important. And so in terms of these structures, no matter what is the case, no matter what craziness is in there, the two parts that we're always going to be looking at are kind of from the end and a little bit away from the end. A little bit away from the end will tell you the carbon in what's called the main chain, the number of carbons in the main chain. So in this case, but corresponds to 4. And then the ending is always going to tell us about what I call sexiness, but otherwise known as functional groups. And it turns out something that ends in ene, you remember those alkenes from the last lecture, which were carbons that are double bonded to another carbon. Also, anytime there's any kind of sexiness in something or anything unusual in something, there's always a number that corresponds to the carbon at which that particular sexiness is. So that double bond is going to be on carbon 2. What the heck does 2-butene look like? Well, there's one representation of 2-butene. You'll notice, first of all, those 4 carbons lined up. And if you number these carbons 1, 2, 3, 4, you'll notice that it's telling us that carbon 2 is where that double bond is. So as I said, chemists have developed all kinds of different ways of envisioning these molecules. And one of the things you'll notice about hydrocarbons is that they're always going to be kind of like the backbone of just about any organic molecule. So chemists start to get pretty lazy about always drawing out these hydrogen bonds. So one way that we can show this is with I guess it's kind of called a semi-condensed structure. You'll notice that that means the exact same thing as the other structure, but it's got a little bit, it's simplified a little bit in that it groups the hydrogens together. So this thing, oops, it's kind of overlapping a little bit. I'm too lazy to actually fix it. So you can just see that if you remove those little bonds, you can get to something which is kind of a more condensed structure. And there's an example of that on that whiteboard activity that I'll go through at the end of class. And also sometimes organic chemists like to put little squigglies in there. Sometimes they show squigglies a little differently. Sometimes they get really lazy and they only label the end. You'll notice here that anywhere that there is kind of this like bend in the chain is understood to be a carbon with however many H's it needs to ensure that it is bonded 4 times. This is the way that I generally show hydrocarbons, and you'll notice that really you don't draw any carbons. It's just understood that wherever the end of a line comes is a carbon with all of its hydrogens. and wherever there is what's called a vertex or a bend in the chain, there's a carbon. For the beginning, at least, I would definitely kind of err toward showing all of the hydrogens just until you start to get to the point where you can kind of see things that aren't even there. A couple other ways, not to overwhelm you, but sometimes if you have some sort of hydrocarbon that has a whole bunch of different carbons listed out, sometimes you'll see this like slightly different condensed structure. This is something that we saw a lot more before there were really good structure drawing programs. Like for instance, you could do this on a typewriter pretty easily, but this is still seen, and I think in your book there's a little bit of that. But if you ever have a question about that, please ask me. I'm going to definitely probably draw things more like these structures right here. So see if you can draw pentene. If you'd like to pause it, feel free. So the real question is when we draw pentene, where the heck does the double bond go, right? So you actually have to differentiate where that double bond goes. And the way that we're going to do that, so this is one example of a pentene. So how would we actually name this? The way that we're going to name this is by ensuring that we get the lowest number on the highest priority weirdness. So this thing becomes 1 pentene is the way that they work. This slide has an animation that shows something that's a little bit more complicated. And this is something with what's called side chains or alkyl groups. So here we have something that you'll notice that there's a certain branching pattern, right? It's not just a simple linear structure anymore. So anytime we see something like this, I always think of this as finding the longest carbon chain that includes all the weirdness that we can possibly get. And what I mean by weirdness are any kind of weird functional groups that aren't just carbons bonded to carbons or carbons bonded to hydrogens, right? So this thing doesn't have any kind of sexiness. So it turns out we're just going to look for the longest carbon chain. And when we do that, we label it. And what you end up doing is that you have these kind of like unlabeled green side chains off of there. So it turns out that these are called methyl groups, and there's 2 of them, and they're on position 2 and position 3. So the name of this is 2,3-dimethylpentane, right? Methyl corresponds to the side chain. The di corresponds to the fact there's 2 of them, and then anytime you have anything that is hanging off of your parent chain, you have to give that numbers in terms of the location. So that would be carbon 1. That would be carbon 2. That's carbon 3. Therefore, this is a 2,3. Notice that I did not number the chain 1, 2, 3, 4, 5, because that would have ended up with giving us a 3,4-dimethylpentane, which is not following that rule that says that you have to give the lowest number that you possibly can to certain things. So when I first started naming hydrocarbons, I was given all these different rules, right? Look at all these things, right? Well, wait, there's more. Right? There's a whole bunch of rules. And so I printed out some of these. If it's helpful to you, I think it's much better to actually just learn by doing. So that's what we're going to do for this very first kind of semi-challenging naming problem. Right? So here is some kind of compound that we need to name. Right? And so what I do is I say, okay, is there anything that is not just a boring carbon-carbon single bond in here? Well, absolutely there is. There's this alkene, right? So we know this thing is going to end with an ene. And by the way, every type of functional group has a different ending, which we'll learn as we kind of introduce these things. And so we know the ending. There it is. We know that it ends in ene. The next thing we need to do is we need to pick out the longest carbon chain that includes all the weirdness. So in this case, I could take this thing, right, and call it, I could call this, let's say, a butene. But wait, I can't call it a butene because 4 carbons is not the longest carbon chain that includes all the weirdness. It is, in fact, a chain that kind of follows my cursor here. Lots of jiggles and jaggles and all kinds of other crazy stuff. And so when we determine that longest carbon chain, I call that step circling the sausage, right? Once you circle the sausage, you've got your parent chain. That automatically is assigned a numbering system, which will look like this in this case, to give the alkene the lowest number you can. And so we end up with a 1-hexene, right? The problem is there's all kinds of stuff hanging off of your sausage. So the stuff hanging off of your sausage, you got to give some sort of name to. Turns out that we have a couple of different side chains. One is called an ethyl group. Right? So there you can kind of see that there's 2 carbons in a row hanging off of something. These two are both methyl groups. So how the heck does this all come together? And I'll show you. First of all, and I don't really care about this rule, the fact that you put things alphabetically. I should mention that the people that came up with this are called the International Union for Pure and Applied Chemistry, which is the IUPAC. And I had so many problems with these folks in graduate school, I started to call them the International Union of Pissant Chemists, because there's all kinds of these rules and they're really dogmatic about it. For you, if you can name a parent chain, throw in a couple of properly named side chains. I don't care if you alphabetize it. And I don't care if like you have a dash where you're supposed to have a comma or anything like that. As long as you can kind of communicate and recognize things, that's kind of what we're going for here. So anyway, of course, there's a whole bunch of different rules, but this is what the name ends up because we have an ethyl side chain on carbon 2. We've got 2 methyl side chains on carbon 4, which means that it gets the prefix di if there's any more than one. And we get a 1-hexene for reasons that we talked about before. So just for kind of quick practice, you can stop if I'm going too fast. But a propene is going to look like this. A 2-butene is going to look like this. Oh, one of the things I should mention about propene is that you'll notice that with 2-butene, you had to include a number. Propene, though, you'll notice that regardless of where we put this double bond, it's always going to be at the end of the chain. So that number is actually not needed. For you guys, though, I would say that's just kind of a super special example. I would always include a number with anything that's unusual in a compound. It's not wrong. So if you want to pause the video, draw yourself 2,4-dimethyl-2-pentene. Hopefully you'll come up with something that looks like this. And this next one is a 1-butyne. Here are a couple more practice problems. And on to the whiteboard activity. As we start this activity, I think it is probably a good idea for you all to have your hydrocarbon prefix guide available to you. And also, I think it would be a good idea to have your full printout of the hydrocarbon drawing and naming resource guide. What I thought I'd do with this series of videos is just to kind of show you how to take things that are a little bit more complicated than stuff that we've seen in PowerPoint slides, and to take, let's say, the name and turn it into a structure, or taking a structure and then turning it into a name. I just thought I'd work through a couple. If you'd like me to work through a couple more in office hours, I'd be happy to. As I said, these are going to be a little bit harder than what we saw in lecture. So one of the very first things that we should do is that we always start at the end and recognize that, well, this thing is an octyne. An octyne tells you two things. It tells you the parent chain, or the longest carbon chain that includes all the weirdness. And it also tells you about the weirdness, or what we call functional groups. In this case, we've got a YNE ending, and that corresponds to what's called an alkyne. And so you'll want to remember from your lecture slides what an alkyne is. And it turns out that it is, in fact, a triple bond, or a CC triple bond. So the first thing that I do, or I suggest doing, is you start with your parent chain, and you just simply take it and write it out in a linear chain. 1, 2, 3, 4, 5, 6, 7, 8. Very next thing I'd do, just to as kind of a reminder to myself, is I would write in the carbon number. In other words, give each one of these a number corresponding to its position on the chain. And we're going to erase this later to clean it up a little bit. But now I've written this thing, by the way, left to right. I could have drawn it right to left if I wanted to. There's no reason I couldn't have done that. Another thing I could have done is I didn't have to show it as like a chain. I could have put like kinks in the chain. Like for instance, let's just I'll show you up above what I'm talking about here. So like if I wanted to be a crazy person, I could have put 8 carbons together like this. 1, 2, 3, 4, 5, 6, 7, 8. Turns out that as long as I've got 8 carbons in a chain, it doesn't really matter. But that seems a little crazy to do that, so let's not. Okay, so back to the question. Once we've got our parent chain, we make sure that we include any sexiness that might be there. One of the things that you'll notice is that we have got sexiness written at the end here, which is a YNE, and we also have a number that tells us where that sexiness is. So what we'll do is we'll come back here and we will put a triple bond in between those first 2 carbons, right? That number always corresponds to the lowest numbered carbon. And the rest of this thing, which is are all side chains in this case, are pictured right here. So these are all side chains that we're going to write off of our main chain here. And so we've got 2 ethyl groups corresponding to the diethyl. They're both at position 3. So first we have to figure out what an ethyl group is. And according to your hydrocarbon prefix guide, that's something with 2 carbons. So what that means is on carbon 3 that we're going to put a chain of 2 carbons. Also on position 3, let me erase the 3 so that it is a little clearer. We've got another chain of 2 carbons. And of course I could have drawn that in any direction I wanted to, as long as it's a chain of 2 carbons. So what I have here is my main chain that I've numbered for you. We've got side chains right here. They're both ethyl groups. So we now have to consider the fact that on position 4, according to this, right here, that methyl, on position 4 there is a methyl group, and we know, because we're masters, that that means there must be a carbon hanging off of that methyl group. And that is almost it. The only thing that we have to do now is we have to make sure that each of those carbons is bonded 4 times. So we go through and we consider each of these in succession here. Well, we've got carbon number 1 bonded 3 different times, and we know carbon bonds 4 times, so we're going to put an H in there. We come to carbon 2, and we recognize that's already bonded 4 times. Carbon 3, I erased the number, is bonded 4 times. The ethyl group carbons, however, are only bonded twice, so we're going to put in 2 hydrogens for that one, and the terminal one is going to get 3 hydrogens. Same goes for this up here. And so anywhere there's just a C at the end of the chain, I'll just automatically put 3 hydrogens in there. We look at carbon 4. Well, that is going to require a single hydrogen. Carbon 5 is going to require 2 hydrogens. Carbon 6, 2 hydrogens. Carbon 7, 2 hydrogens. Okay, so this is a perfectly acceptable answer. It looks a little crazy, but the good news is we've got the right number of hydrogens, right number of carbons. There's all kinds of different ways that we could have drawn this, as long as we keep all the connections the same. I'm just going to show you so that we can get kind of experience with doing this kind of thing, the way that an organic chemist would most likely represent something that looked like this in what's called that really simple skeletal form. So the first thing that you would do is you draw a triple bond. And you'd start off with that very first carbon. That first carbon is going to represent carbon 3. And then you put little squiggles corresponding to your main chain. So let's see, that's 1, 2, 3, 4, 5, 6, 7, 8. And then the ethyl groups you would represent in the same way. And there's another ethyl group. Okay, so just keep in mind, and I'll do this on your celebration of knowledge for today, is that I'm going to primarily use just this really simple skeletal notation because it lets us be lazy. The next problem on the sheet is I got a couple of little minor differences here, but you'll notice that I'm going to follow the exact same pattern, which I'll kind of fly through a little bit faster now that we've done it once. First thing that we do is we notice the parent and any sexiness that might be in there. So now we've got a cyclohex something or other. So keep in mind that cyclo corresponds to a cycle. So when we're doing our carbons, we will draw a 6-membered ring containing 6 carbons. So that is the cyclo and also the hex part. And then somewhere in here, and well, let's just number the carbons like I did in the last slide. So we'll call that 1, 2, 3, 4, 5, 6. We'll go through and we'll say, okay, carbon 1 now is going to be an alkene. And we know that an alkene has 2 carbons. So I have to put it between the 1 and the 2. So now I have got a 1-cyclohexene, and then anything else will be written out in front. Like for instance, this 1-propyl. And we know from our guide, first of all, that a propyl group is 3 carbons, and the fact that it is on carbon 1 is told to us by that little 1. So we will put a propyl group of 3 carbons right here. Next thing we're going to do, and in this case I'm going to erase all the numbers because once we've got everything finished and we're on this final hydrogen step, all we're going to do is fill in all the hydrogens. Keep in mind carbon bonds 4 times. So it should look like this. So there's our structure. And if we wanted to be cool kids and show what that sucker looked like in a skeletal form, we would draw something that looks like that. So 2 different forms, right? 1 propyl, 1 cyclohexene in 2 different forms. What I would do if I were you, before I attempted the homework, by the way, the homework I think has easier examples of these, but I would try the next 2 names and try to convert them into structures. And if you have any questions, feel free to ask me. Okay, now we're going to reverse the train a little bit, and we are going to take structures and turn them into names. And I'll show you some of the ins and the outs of this. One of the first things that I kind of worked hard on in this handout is I gave you a couple of different ways of representing organic compounds using all kinds of different structure conventions. So here is the very first one. One of the things I would probably recommend, first of all, maybe I'll make this bigger. Okay, now that this is bigger, first of all, you'll notice that this is a skeletal structure. And so one of the first things I like to do is to circle the longest carbon chain that includes all of the weirdness. So as I'm going to circle here, I know that this is certainly weird, right? So I have to include these in my parent chain no matter what I do. And now I come to this dividing line, and I'm going to choose the path that gives me the most carbons. So this is the longest carbon chain that includes all the weirdness. The very next thing I'm going to do, I'll use a different color, is I'm going to number the carbons here. And the rule is that I have to give any weirdness the lowest number that I possibly can. So in this case, I'm going to go through, I'm going to number my carbons. That'll be 1, 2, 3, 4, 5, 6, 7. And so we now know a couple of really important things in terms of the name. First of all, we've got something that is 7 carbons. So this is automatically going to be some sort of hept. And we've got 2 individual alkenes. So every alkene ends with ENE, as we talked about before, but now there's 2 of them. So we're going to call this a heptadiene. And as we said before, anything that is kind of unusual, we have to give a number for, and we have to give it the lowest number that we possibly can. So in this case, this is a heptadiene, but even more than that, it is a 1, 3 heptadiene. 7 carbons, 2 alkenes on positions 1 and 3. And anything else that is not included in this name, and let's use this color right here. I like to circle also, maybe with a different color, just to show you all that it's not part of the main chain. And this is, of course, a single carbon. And so if we look at our hydrocarbon prefix guide, anything with a single carbon is giving a meth. And we also have to give the position where it is, and it's on position 5. So we are going to call this a 5-methyl-1,3 heptadiene. So I'm going to, here's the 1 and the 3, and that's a dash. So kind of tough to see. I probably should redraw it, but I'm too lazy. So 5-methyl-1,3 heptadiene would be the name of that one. For the next one, I skipped down to what's called the condensed structural formula, just to show you how to handle these. One of the things your book really likes to do, even though they've become a lot less popular writing things like this with the advent of structure drawing programs. It used to be really common practice to draw everything in this like single line, and there's a whole bunch of conventions that I don't want you to really have to worry about it too much, but I at least wanted you to have it see one here. So in just to kind of show you what this thing actually looks like, notice a couple of things. First of all, notice that, right, you've got some parentheses and you also have some carbons that I've kind of put there, right? And so I like to kind of start with the things that don't have parentheses so that I can just draw them out. And I don't actually worry about the hydrogens just yet. And keep in mind, all we have to do is name this thing, but it's a pretty important thing to do to start by expanding the condensed formula. So what we have are just 3 carbons directly in a row. That's what the condensed formula is telling us. Now, when you look over here at this set of parentheses and that subscript, what it's telling us is that there are exactly 3 methyl groups on that carbon. So we will draw those 3 methyl groups. 1, 2, 3. And if we go onto the end of the compound and we see the parentheses, those are ethyl groups, and the subscript is telling us that there are 2 ethyl groups hanging off of that very last carbon. So we go through and we just do our ethyl groups at the end here. And that, without hydrogens, is the structure of the expanded structure of that compound. You'll notice, since the question is telling me just to name it, I'm going to be lazy and not include the hydrogens. If the question said to draw out the full structural formula, you'd obviously want to include the hydrogens. But since the hydrogens don't have anything to do with the name, I'm going to do the circle the sausage game, everybody's favorite. All right, and so our job is to find the longest carbon chain that includes all the weirdness. There is no weirdness here. There are no functional groups. There's no alkenes, there's no alkynes, there's not even anything cyclic. So I just pretty much figure out the way that I can get the longest carbon chain, and I have a couple of choices here. The one I'm going to choose, though, is going to look like this. And you'll notice that that gives me a certain number of carbons. In that case, I've got 1, 2, 3, 4, 5, 6 carbons. So this will become a hex with a ending that is just ANE because it's just boring. There's no alkenes or alkynes. So this is considered a hexane. Now the question becomes, which way should I number? Turns out there's a whole bunch of different rules to this, but the way that I need to choose numbering, and I'll just show it to you, is that I need to number starting where I get the number where the branches have the lowest number. So what I must do is I must number 1, 2, 3, 4, 5, 6. If I had numbered the other way, 1, 2, 3, I would have gotten to this point where I've got an ethyl group on my third carbon, and that would be bad mama jamba. Maybe I should actually show you that. And I'll choose a different color. Let's see, I'll try blue. So if I had numbered this way, 1, 2, 3, you'll notice that that very first point of difference right here, it happens on carbon 3 relative to the one that I showed you before, where the first point of difference is on carbon 2. So what that means, and let me clean this up a little bit. So what I have here is I have got 2 methyl groups that I've circled. I've got a single ethyl group that I've circled. So this is an ethyl. These both are methyls. Because there are 2 methyls, those become a dimethyl. So when I finally go back and I write out my name, for weird reasons that I don't really care about, you have to alphabetize these things. Well, you don't have to, but I do. So since ethyl is before methyl in the alphabet, that's what they call that thing, you actually have to list that first, and then you would then put in the other group here, which is a 2,2-dimethyl. Wow, that looks very clear. So 4-ethyl 2,2-dimethyl hexane is the name of that. So I've written it out for you right there in a little bit more clear fashion. Okay, well, with that said, I'm sorry it was a relatively long lecture today, but I thought it'd be important to kind of get all of this together before the weekend so you could practice over the weekend and also practice on your homework. If you have any questions, I'll be keeping an eye on Canvas. Let me know.